Hello, I'm Tyler Newberry. I'm a mechanical engineering student at the University of Nevada, Reno. This is my intermediate heat transfer project on hydro flasks. Being as the times are uncertain with coronavirus, we do not have access to lab or university materials at the University of Nevada, Reno. So I was left looking around my house for a heat project example. I didn't have to look too far before my eyes stumbled upon my trusty hydro flask sitting on my desk. Thinking more about exactly how hydro flasks work, I've always been amazed at how well they insulate heat inside of them. Looking into the technology, it's anything but new, dating all the way back to the 1890s when it was first used. And then first popularized by the thermos flask in the 1960s, and then later again by Hydro Flask, and now you can see them running all around university campuses. But how exactly do they work? They work by having a vacuum-sealed insulation between two different materials. This effectively reduces the conduction and convection inside of the hydro flask to zero, while keeping the radiation transfer low by using low emissivity materials such as stainless steel or glass. In the case of the hydro flask, stainless steel is used because it's not as brittle and breakable as glass. However, it does have slightly higher emissivity. So, first to move on with the experiment, we will conduct this analysis through theoretical means using mathematical examples, and then through experimentation, as well as a finite element analysis. First, with the theoretical analysis, we find that the radiation heat transfer is equal to the interior area times the emissivity times the Stefan-Boltzmann constant, and finally times the differential heat quadratic. The interior surface area is 68,300 millimeters squared, and the average emissivity for stainless steel is 0.54. This is not a tested radiation equivalent for the stainless steel used in the hydro flask, however, an approximation used by stainless steel in general that was found. Solving for these constants, we find that the total heat transfer throughout the hydro flask is 1 kilojoule of heat. This, however, is very limiting because we are only looking at the radiation heat transfer throughout the hydro flask. This does not take into account the conduction through the lid of the hydro flask or through the lip of the metal in the hydro flask. We will see that later in the experimental analysis. Here, we can see the experimental analysis. To conduct this analysis, we first boiled water and then poured the water into the hydro flask. After the water had heated up the interior volume of the hydro flask, we could see that its initial temperature was 90.5 degrees Celsius. Thereafter, we took temperature recordings every 30 minutes. We chose this method because it was easily conducted using nothing more than household materials using a kitchen thermometer. Every 30 minutes was chosen to limit heat loss through opening the lid, yet have fine enough resolution to see the heat decay out of the hydro flask. After this, we simply solved for the MCAT equation using the heat constant of water, the mass of the water, and the temperature lost. Solving for these variables, we found that there was 27 kilojoules of heat lost through the hydro flask over the course of 2 hours. Now, this is much larger than the 1 kilojoule of heat loss that we saw in the theoretical analysis. This is largely due to the fact that most of the heat lost out of the hydro flask is through the lid of the hydro flask, where it's most inefficient. The radiation efficiencies of the hydro flask are very large. However, most of the heat loss is through the top. We can see this with the thermos flask. Thermos is an older technology dating back to the 60s. However, they got it right because they actually used a stopper that is much, much thicker than the hydro flask. This stopper is almost 2 inches thick compared to the 1/4 inch stopper on the hydro flask. They did this because they knew that this was the largest inefficiency in their thermos, and which leads to much larger efficiency in the overall container. However, hydro flask chose a thinner lid because they wanted more convenient over the performance gains that they would have gotten through a thicker lid. A common design trade-off that many engineers face. Reflecting on that, we conducted finite element analysis, and we saw that our assumptions were correct, that most of the heat loss is through the lid of the hydro flask. The radiation throughout the walls of the hydro flask is very minimal and is very efficient. As you can see that the heat distribution keeps all of the heat in the lower parts of the hydro flask. One possible answer of why Hydro Flask did this is because when you are carrying your Hydro Flask vertically, all of the water falls to the bottom, and that's the most efficient part of it. If you were to carry your Hydro Flask upside down, however, the heat would be conducted much faster through the lid because it's in direct contact with that. Here you can see another example. This image was sourced online of a thermal camera seeing two different Hydro Flasks. As you can see, the walls of the Hydro Flask are very efficient on the left specimen. However, the lid is giving off lots of heat loss because of the lack of insulation in the lid. Also in this image, you can see that the right one has a much higher temperature. This is because of the seal that was lost in this. This is an example of how much difference that vacuum seal actually makes in the conduction and convection heat transfer coefficients. Overall, throughout this experimental analysis, we have found that it is very hard to theoretically analyze real-world models of how heat transfer will work. And overall, it is amazing to see that something that you use every day has such a big influence from heat transfer and heat transfer design.